So we're going to start this video with hemodynamics. Hemodynamics is a physical understanding of the factors that govern blood flow. And so these are some of those factors, the same factors that govern the flow of any fluid. And this is a variation on Ohm's law. And Ohm's law is I equals delta V over R. So current equals the change in voltage over resistance. Now, flow is going to replace current, I, and delta P, which is the pressure gradient, is going to be changing the voltage differential. So delta P is going to change delta V. And delta P is the pressure gradient, which is the arterial pressure minus the venous pressure. Now, arterial pressure is the pressure in the left ventricle, or the pressure in the systolic pressure in the aorta, and the venous pressure is the pressure in the pressure in the right atrium, or the pressure that is that needs to be overcome, or the pressure that is the pressure that needs to be the pressure drawing in blood into the heart. So the pressure coming into the heart versus the pressure leaving the heart. So the pressure going out versus the pressure coming in. So that is, and resistance, however, is still resistance. The resistance will always be resistance. Now, this is driving pressure. We will have our aortic pressure and our right atrial pressure leaving versus pressure entering. Our average systolic pressure is going to be about 120, and our average venous pressure, the pressure entering the heart from our superior and inferior vena cava, is going to be between -4 and 4 millimeters of mercury. It's going to be 0, effectively. So that means that our driving pressure, our delta P, is going to be our right atrial pressure. That's going to be 120 minus 0. That's going to be 120. Now, our heart sides. Our right side of the heart is going to receive our systemic circulation, and it's going to send our pulmonic circulation. Our left side is going to receive pulmonic circulation and send systemic circulation. We'll have thinner ventricle walls in our right side than in our left side. The question is why? Now, the reason for this is flow needs to be equal. The rate of flow, the actual movement of fluid in milliliters per unit time, needs to be equal in the right side of the heart and the left side of the heart. Otherwise, one side will move blood faster than the other side, and you'll have a backup of blood in one circulation versus the other. So if there is too much blood in the systemic circulation, you'll have edema in the legs and arms and various other body organs. And if you have too much blood in the pulmonic circulation, you will have pulmonary edema, and you'll have it very difficult to breathe. So one way or the other, the flow needs to be equal. You need to pass blood through both sides of the heart at the same flow rate. And in order to accommodate that, you need one side to have the same, or each side needs to overcome different resistances. So the pulmonic system has a lower resistance than does the systemic system. The systemic system includes your head, your arms, your chest, your abdomen, all of your vital organs, your lower extremities, the genitals. All of those different organ systems are in your systemic system. And that has a total peripheral resistance that is significantly higher than the pulmonic resistance. So if your denominator, the R value, if the R value is larger on one side, then that means the driving pressure on the left side, which is sending to the systemic system, needs to be significantly larger. In order to generate that pressure, you need larger muscle. So, if the resistance on the pulmonic side is lower, a smaller denominator, the driving pressure should be smaller in order for F to be equal on both sides, F right and F left. So if F right and F left are equal, and R right and R left are different numbers, that means that the pressure, the driving pressure, needs to be different on both of these sides. So the right ventricle needs to generate a lower pressure than the left ventricle does. In order to generate a lower pressure, those walls, those muscular walls, need to be thinner. And these muscular walls need to be thicker. So that's why we have these different thickness of walls. Now, another reason, or perhaps a consequence, of the capillary structure of our alveoli in our pulmonic circulation, we don't have the same toughness of the capillaries in our pulmonic circulation. There is no medarterial and thoroughfare channel system in place in our pulmonic circulation. We just have pulmonary circulation coming in and then exiting. There is a site of partial occlusion, but there is no individual precapillary sphincters and a medarterial system. There is no way to shunt blood here. So there is no medarterial and thoroughfare channel capable of handling higher pressures. These delicate capillaries could rupture if arterial pressure were to suddenly increase, if that driving force were to increase at a rapid pace. So if we damage those vessels, that's all that you're going to get. Now, that brings us to the question of why are the atrial walls needing to be thinner than the ventricular walls? And it's the same reason here. The flow rate needs to be the same. So if we have a pressure exerted by here versus here, we need to have our pressure be lower in the atrium in order to receive blood from the systemic or pulmonic circulation. The receiving of blood needs to have a low pressure, from high pressure in the circulation from the veins to a low pressure in the atria to receive that blood. And then they need to pump into a relaxing ventricle in order to overcome whatever pressure is in that ventricle. And overcoming that resistance is significantly smaller. So these ventricles have to overcome a lot of resistance in the systemic and pulmonic circulations, but they do not need to overcome that same level. Pause the video.